Okay, I wanted to also make a point. So the overall structure, so this talk of like SPDNF really shows up in the overall structure of the periodic table. So I want you to imagine that the HE is over here, right? So then this block of the periodic table corresponds in a way to the s orbitals. This block corresponds to the p orbitals. Here we have the d orbitals. And then here we have the f orbitals. So for this reason, often this would be called the s block, the p block, the d block, and the f block, right? Okay. Another point I want to make is that you might notice, so basically this really goes in here. Let me clear everything. Right. Okay. Okay. So see, the F block really belongs in here. It's just that if you were to do that, the periodic table would be like super long. So the order goes cesium, barium, then so cesium, barium, lanthanum, cerium, praseodymium, etc., etc. Right? So it doesn't go straight from barium to hafnium. Okay? I just wanted to make that minor point. Okay, so this electron configuration stuff is actually really important. So I think it might be a good idea to do another example. So let's do a slightly harder example. So let's go with chromium. Okay, chromium. So now we don't want to have to write out the entire electron configuration of chromium, right? Because that would be pretty long. So what I want you to notice is that when we do chromium, we're basically taking argon, which I've circled here, and then we're adding more and more. We're just adding electrons to like the electron configuration of argon. So to make life easier, what we can do is we can abbreviate this as argon and then proceed from there. Okay. So, okay. So here we have like the 4s orbitals. So then what follows the 4s orbitals? Does someone want to tell me what follows the 4s orbitals? Like what do we fill after the 4s orbitals? Right. So we fill the 3d orbitals. So, okay. So first we put 2 electrons for the 4s because 2. Then we have 3d. Now we need to figure out how many d electrons there are. So 1, 2, 3, 4. And oh, I just realized that chromium is a bad example. Okay, so this is the predicted electron configuration for chromium. In reality, it's 4s1, 3d, 5. And this is one of the quirks I was talking about earlier. See, there are some quirks. Yeah. So this is just one of those rare exceptions to the order that, I mean, I've memorized them because, yeah, but you don't need to memorize that. Okay, so maybe sometime later, if we have time, we can talk about why these exceptions arise. Okay, so let's do another example to make sure. So I've done this example for you. So I want you to do an example. So let's do selenium, right? So can someone type like the electron configuration of selenium? So here we have the filling order, if anyone. Let me see if we can copy this. Okay. 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 So Brian, you're close. So when we do these noble gas configurations, we only abbreviate the noble gases here. Yeah, we only abbreviate the noble gas part, and we still have to write out all of this stuff. Okay. So yeah, so Karen has got it. So yeah, so we start from argon, and then we do the 2s, then we fill the 3d here, then we have 4 p electrons here. Okay, now let's do a hard one. I think y'all are starting to get this. Oh. Okay, so I have, let me get the periodic table back up. One. This is surprisingly difficult. Okay. So this way we don't have to switch around. And just got rid of the chat. Okay. So let's do okay, let's do like promethium. Let's do promethium. Promethium is an interesting element. So it turns, did you know that there's no stable isotope of promethium? So all promethium atoms are radioactive. So, which is very strange since none of the elements near promethium are radioactive. It's just promethium. So does someone want to give me the electron configuration of promethium? So just as a reminder, and then this loops back around. This might take a while because it's okay. Let me check. Okay, yeah. So that's it. So xenon and then 6s2 and then 4f5. Okay. So do I need to? Okay. Oh, minor point. So there's some weirdness with the lanthanides, which is why I tried to pick this one carefully. It turns out that for lanthanum, cerium, and praseodymium, these three, it's 6, and then this one is more like, these ones have the form, and then 2, 4, 5, 1, and then the 4f. And then I don't think that applies to the rest of them. But yeah, it's just basically by this point in the periodic table, like these electrons are kind of far away from the nucleus. and all the energies are close together. So sometimes the d orbital just borrows an electron from the s orbitals. So, but that's not really a significant point. So I wouldn't worry about that too much. Okay, so now we can talk about monatomic ions. So basically, here, the major idea is that an atom, to be more like stable, it wants to achieve what we'll call a noble gas configuration. So it wants to have the electron configuration of a noble gas. So to do this, we add or remove electrons. And so this is really what chemistry is all about. Chemistry is really all about the movement of electrons. And if you eventually go on to study organic chemistry, you'll really see this. Because when we draw mechanisms, we draw the movement of electrons using, and we represent this using arrows. So we don't want to touch the number of protons, because if you change the number of protons, you're changing the element, right? Because the element is really defined by the number of protons, the top number. Also, the protons are within the nucleus and they're held together really, really strongly. So it takes a lot of energy to remove protons, or to add protons to remove them. So no, we don't do that. All we do is we add and remove electrons. So let's do an example. Let's do lithium. Right. Okay. So let me delete some of this stuff. Okay. So can someone tell me the full electron configuration of lithium? So lithium is here. Right. Okay. Yep. 1s2 to s1. So I'll write that down. So okay, so now we have this basically incompletely full orbital, right? So in order to get to the electron configuration of a noble gas, either we can add 7 electrons or we can remove 1. Well, if you remember to what we talked about earlier, all of these electrons repel each other. So it's really energetically unfavorable to add more and more electrons to an atom of lithium. So instead, it's much more energetically favorable to just remove this electron. And now we're left with 1s2, which, if you remember, is just the electron configuration of helium. Okay, so now we have this chart. We now have a lithium atom with -1 electron. So considering that electrons are negatively charged, what do you think the overall charge on this lithium atom will be? Yep, so it's going to be +1. So look at the atomic number of lithium. So we have 3 protons, which are each +1. And since we started with 3 electrons, but now we have 2, so we have 2 electrons. So that's, and each one of those is -1. So if we sum that all together, we get a +1 charge. So, so we write this ion as lithium plus. And some people like to write the plus in a circle, so I'm one of those people. So, yeah. Okay. So I had a picture of this. So as you can see, so notice all of the elements in the group, at least for the main group's elements, which are at least for the ones near the edges of the periodic table, they tend to all form the same ions. So notice how, oh, I forgot, I'm not drawing. Let me annotate this. Okay, so all of these are 1 plus, right? All of these are 1 minus. All of these are 3 minus, right? So the idea is that elements in the same group, oh, by the way, so columns are called groups, and then rows are called periods. So all of the elements in the same group tend to have somewhat similar properties. Yeah, and we'll talk about this a lot when we talk about periodicity. So let me clear all of this. Okay, let's do one more example. Oh, okay. Let me get rid of all of this. Okay, so let's do sulfur. Let's do sulfur. So sulfur is so just for convenience, neon 3s2 and then 3p. Does everyone agree with that? Right. Okay. So how do we achieve a noble gas configuration? How do we get the electron configuration of a noble gas? Well, either we can just remove we can just remove 6 electrons, right? So we could do that. But the problem is that all of these electrons are attracted to the nucleus. So removing all 6 of these electrons would require a huge amount of energy. So it's just not an amount of energy that's feasible in a chemical reaction. Maybe in like a particle accelerator you can do that, but not in a chemical reaction. So instead, let's look at the closest noble gas, argon. So argon is neon, and then 3s2, 3p6, right? So in order to get from this to that, how many electrons do you think we need to add?